Greetings, calculus students. Welcome to my favorite episode of this series. We get to take a step back from all the sequences and series and sums and convergence and all the tests. We're done with the tests. You must be happy about that. And we get to talk about something that's really mathy important. And it's this kind of it's this area of math that you haven't thought about at all up to this point. Let's think about what the big idea of calculus really is. What unites a derivative and an integral and infinite series and the idea of a limit. It's this idea of not being able to know something. It is physically impossible for a line to have slope at one point, but the derivative does it anyway. It's impossible to add up infinite little tiny things, but the integral and infinite series do it anyway. And a limit is saying we can't actually get there, but we're going to say we can get there anyway. Calculus is about getting really close to stuff that is impossible to know. And now I'm going to ask you a question that at this point we have no way to answer. What is sine of 1/2? Simple. What is the sine of 1/2? Not the sine of pi halves. You know the sine of pi halves. The sine of pi halves is top of the unit circle, 1. What is sine of 1/2? Well, how would you find out? You'd plug it into a calculator, but how does your calculator know? We know that sine looks like this, but we only really know these points. Why do we know what sine is? How can we tell exactly what is right there? How do you know what sine of 1/2 is? How does your calculator know what sine of 1/2 is? And the answer is it absolutely doesn't. It has no idea what sine of 1/2 is. What it can do is guess. Your calculator can approximate to a very close margin sine of 1/2. But no one actually knows what sine of 1/2 is. You just guess. You approximate to very close. And that's super cool. And you can do it with calculus that you learned months ago. You don't really need all of this sequences and series stuff necessarily to get a pretty good approximation of sine of 1/2. And let's talk about how to do that. So if we've got our sine wave, we know that sine looks a little something like that. I'm going to extend it in this direction too. That's pretty good. We've got our sine, and we know a couple of these points, as we've established. So one way to approximate what sine is if we say, well, what if we're pretty close to 0? We know what sine of 0 is. Sine of 0 is 0. And so if we draw this line, it's right over the axis, that's just a constant. That's just y equals 0. Then it's a pretty bad approximation for sine, but when you're really close to 0, it might kind of work. And that's because we have matched the value of sine at 0. Now I'm way off to the side. I've not centered this. Because we've matched the value of sine at 0. Now, there's another step that we already know how to do that is one further than matching the sine. What if we drew a straight line and we matched the value of sine at 0 and also the slope of sine at 0? And so our line would be, we know that our line passes through 0, 0, and our line has slope of the first derivative of sine, right? The derivatives match because they have the same slope. So sine of x, the first derivative of sine is cosine of x, right? This is f prime. Here, the whiteboard is shaky today. So f prime of x is cosine of x, and cosine of 0 is 1. And so this has a slope of 1. And so if we have a line that goes through 0, 0 and has a slope of 1, which is just the line y equals x, then we'll have something that looks like that. This marker is giving up a little bit. But you can see how that's kind of close at some points. Like, there is this region still very close to 0, but there's this region where it's a pretty good approximation. And this is the linear approximation that we learned a while ago in like Calculus 1. This is a way to find values that are pretty close to the answer, as long as you're pretty close to the point that you centered your approximation at. Because we've matched the value, which maybe you could think of as the 0th derivative, and you've matched the first derivative, the slope. And so then you start thinking, what if we match the second derivative? Well, what does second derivative represent? Second derivative is the rate of change of the first derivative, so like, how curvy is it? What if we match the curviness? Now, the second derivative of sine of 0, well, it has a slope of 1 and is going pretty straight right there. And if we actually do it out, f double prime of x, oh, I remember why I was standing on that side, because it's harder to write on this side. F double prime of x is back, it's now negative sine of x, but negative sine of 0 is still 0. So it doesn't have any curviness right there. So we're actually doing pretty good, but then we can do third derivative and fourth derivative, and they start becoming harder to visualize. And so it's more difficult to like think about what you're actually doing when you're adding each of these derivatives. But you understand how like each time we add a derivative that matches our original function, this line that we're drawing, this approximation, is going to bend closer to our original function. Like if we were to take the third derivative of this, I've now run out of room. Okay, I'm actually, let's build this approximation from the beginning. So our approximation, I'm going to use the letter t, and I'll tell you why I use the letter t in a second. This is t of x centered at 0. This is called the Taylor polynomial. It's written up there, so I guess I wouldn't withhold that information from you. But I'll talk about that in a second. We know that we want our approximation to have the same like value at the center. And so like the y-intercept, basically, the one that doesn't have any x terms, this constant term, has to be this function. So f of x equals sine of x. F of 0, our Taylor polynomial, also goes through that. And then we add a term, because when we make the first derivative of this, we want the derivatives to match. So we add our new term. First derivative of a constant goes away. So our constant is gone. So we don't really have to worry about that in order to match our derivative. We just say that we want it to match the first derivative of x at 0 times x. And that x is there so that when we take our first derivative, the x goes away, and it says that the derivative of our approximation is f prime of 0, which is the derivative of our original. And then we add our next term. And we want this next term to basically be f double prime of our approximation. But in order to make it just equal f double prime, when we take the second derivative? Well, we take one derivative, and so I'm going to go here and say we're t prime of x, one derivative. This goes away, and we just have f prime of 0. And then our second derivative, that'll go away. But we can't just put this here because we need it to withstand like two derivations. So when we take the first derivative of something, the x goes away. But if we just put another x here, then on the second derivative, it would be gone. And so if we put an x squared, then our second derivative is going to be, first derivative, you pull out a 2. Second derivative, the x goes away. But then our second derivative would be 2 f double prime of 0. And so we have to compensate for that. So our next term is actually 1/2 f double prime of x squared, right? Because each time you derive this term, it's going to, this 2 cancels out that 2 because of the power rule. And then if we keep going, we want the third derivatives to match. Now, we know that we'll probably need some constant to cancel out all our derivations. We're going to need the third derivative, an x cubed, so that by the time we've taken 3 derivatives, it's a constant. And what do we need here? We take the first derivative of this, and you pull out the 3. So you get 3 f triple prime of x squared. And then you take the second derivative of this, and the square comes down and makes this 6 f triple prime of x. And then the next derivative, the x goes away. And so it isn't just counting up. It isn't just going like 1, 1/2, 1/3, because there's that power rule where you're getting 3 pulled down and then 2 pulled down. This actually has to be 1/6. And now we can start to see a pattern emerging for how we build these approximations. We can start to say, well, each time we're taking a higher order derivative. Each time we're raising the power of our x. And each time there is this coefficient in front of it that is determined by the power rule. And what is the power rule doing? Well, it's multiplying this coefficient of x by then the next number lower than it, because we've taken the 3 down and we've subtracted 1 to make it 2. And then we're taking the 2 down, subtracting 1 to make it 1. And then we're taking the 1 down, in essence, when we're taking the last derivative. And that, we've got a name for that. We call that factorial, right? It's some number multiplied by every number lower than that number. And so we've basically come up with this pattern that generates an nth term. We have our general term for this approximation. We can say that a sub n, the general term, equals the nth derivative. Remember that when you put parentheses around this, this isn't an exponent. It's the nth derivative of wherever we've centered our equation, right? Here we've chosen to center it at 0, but you can choose to move this center anywhere you want. Times x to the nth power, right? Each time we're counting up. And then there's this divided by, here actually I'm going to move this around. It's not normally how you see it written. The nth derivative of f, 0, or our center, divided by this factorialized number that we're getting from the power the power rule. So this is n factorial times our x to the n. And so this is actually, we've just come up with this general way to find the approximation of anything. Because notice I've stopped really caring that this is sine of x. Right, like we're not really using signs in this, we're just using f's. The only thing that isn't general is the fact that I've declared our center as 0. But what if we wanted to move the center around? What if we didn't want it to be centered at 0? What if we wanted it to be centered at here at like pi halves or here at pi? We can move that center anywhere. We just say that this, right, each one of these values of these derivatives, we want to be equal to the value of the derivative there. So we call that our center. And then we do have to do a little bit over here, because remember when you're like shifting a function around, to shift it forward, you have to put subtraction within the parentheses, like next to an x. So this is like back from transformations. We have to go x minus our center to the nth. And now we actually have a general equation for approximating any function we want at any value we want. So let's try plugging in something. Let's try a different function, no longer sine of x. Let's try another thing that we use a lot, but we don't actually know what it is. Let's try e to the x. So if f of x equals e to the x power. And you're like, well, we do know what that is. It's e to the x power. We know that e is just a number. But e is this irrational number that goes on forever. So we never know exactly what e to the x is. I'm going to shift it forward because I'm standing in front of it again. We never know what exactly these values are. And so we have to calculate it using these approximations. So let's say I would like to make a Taylor polynomial approximation of e to the x. That's what these are called. This is called the general term of a Taylor polynomial. Where do we want to center it? Centering it 0 is really easy. It's so easy that some guy decided to steal it and name it after himself. When you centered a Taylor polynomial at 0, they call it a Maclaurin polynomial. But it's much cooler to call it a Taylor polynomial centered at 0, because Taylor discovered it first. Let's say t sub 0, so a Taylor polynomial centered at 0 of x. And then we just go through with our general term. The first one is the constant term, and so these n's are all 0. So the 0th derivative of the center, we're just going to call, instead of a 0th derivative, we're going to call it, like, the 0th derivative is f of it. Like, it's the value of the function. So the constant term, the value of e to the x centered at 0, e to the 0th is 1. So I'm going to write it out twice, once with like what it is in the general term, and once with our actual values. Then we go to the next one, and we get f prime of 0. 1 factorial is 1, so we don't have to worry about that, times x. And so down here, we're getting, what is f prime? Here, I'm going to make a little list over here. F prime of x, well, it's still e to the x. That's funny. It's actually always e to the x, because e to the x is one of those funny functions where the derivative never changes. It is the function where the derivative never changes. And so no matter what our nth derivative is, this is always going to be 1. E to the 0th is always 1, no matter what derivative you're taking. And so we've got, just again, x. Okay. And then our next term is f double prime of 0, x squared, times 1/2, because of this n factorial. And so we're just going to get f double prime of 0 is 1. And so we're just going to get x squared over 2. And then the next one, maybe you can see where this pattern is going. plus 1/6 f triple prime of 0 x cubed. It's just x cubed over 6 plus, and then the next one is going to be x to the 4th over 24, dot, 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 and so on. And now we've got this approximation. Like if I ended it here, it's a pretty good approximation because we've got all, like as long as we're staying fairly close to the center, this is going to look pretty much like the function. I can't draw it very well, but if you look up pictures of Taylor polynomial approximations, they start to like wrap their way around the function. E to the x, right, looks, what does e to the x look something like? Looks something like that. And so our Taylor polynomial starts out as a line, and then it starts out as a curve that's like that, and then it eventually gets closer and closer until it's basically aligned with our function. And so even just this far, all the way up to n equals 4, which we'd call the 4th degree Taylor polynomial, this is a pretty good approximation because it matches the 0th, 1st, 2nd, 3rd, and 4th derivatives of our original function. But what if we wanted it to be exact? Well, calculus is all about getting very, very close to values we can't get, and then basically pretending they're exact. So what if we just said there are infinite terms in a series? What if we added back those dot, dot, dot? And now you see why this is in our sequences in series unit. Because we can say that if we found this pattern, which is just x to the n over n factorial, we can say that e to the x equals exactly e to the x equals the sum from n equals 0 to infinity, the infinite sum of x to the nth power divided by n factorial. And that is exact. This series will converge exactly to e to the x. And that is cool. Like, that is really fun. And that's not all we can do. Like, you see how simple this is. It's because we found this pattern. Not all equations will give you this pattern, but you can follow this like formula to build something that is very, very close to any equation you want. And some of them are also pretty simple. Sine and cosine also look very similar to this e to the x. I'm not going to do them all out right now, but if you follow these steps, follow that general term of the nth derivative divided by n factorial times x to the n, you get another cancellation out thing. Like sine centered at 0, you saw how every other one, the derivative is 0. So it makes sense that that one would be kind of be alternating back and forth. And it's either 0 or 1, because the first derivative of sine is 1, second derivative is 0, third derivative 1, second derivative 0. And so you get this alternating pattern. So sine is an alternating series. And it alternates between the odd terms of the series, because the 0th derivative is 0, but the first derivative is 1. And so every time n is an odd number, sine gives you basically the same value as e to the x, because the derivative is 1. And so you get this equation, -1 to the n, x to the 2n plus 1. That looks a little bit weird, but all it does is make sure that n is always odd, right? Like n is counting up 1, 2, 3, 4. But this is saying, well, when n is 2, we're actually going to make this 5, because this plus 1 just makes sure it's always odd. Divided by 2n plus 1, all the odd numbers, factorial. And so sine, we see what e to the x looks like. Sine of x is going to look like, when n is 0, it's positive, but this is 1 over 1, 1, plus sine, hold on. That might be, I might be starting at the wrong spot. But anyways, 1, it's going to be negative x cubed over, oh, x to the, that's why. It's because this is x over 1. When this is 1, it's x cubed over 3, or sorry, 3 factorial, which is 6. And then it's going to be plus the next odd one, x to the 5th over 120, dot, 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 dot. So it is the alternating odd terms of e to the x. And then cosine is just the opposite. Cosine is all the even terms, because its even derivatives are 1 and its odd derivatives are 0. So we get a similar sum of negative 1 to the n, x to the 2n, right? Now it's always all even, over 2n factorial. And so this one will be, when n is 0, this is 0 over 0, or 0, hold on. When n is 0, these are 0. When n is 1, oh, x to the 0 is not 0. That's why I was getting confused. 1 minus x squared over 2 plus x to the 4th over 24, etc., etc., etc. And so now we've just defined, like, exactly these infinite series that converge exactly to these 3 unknowable functions. And I think that is super cool. Taylor approximations are awesome. I encourage you to look up pictures, the pictures of it like wrapping around the function, or like you can make this in Desmos and make a slider for how many terms there are and like see how it wraps around the function. It's super cool. This is what the rest of this course looks like. There are a couple more videos just with little things that you can do with these, but basically everything we've been doing, these infinite series, the idea of convergence, the idea of power series, because notice that these are series with x's in them, the idea of alternating series, because there's an alternator. Like, all this is like all building up until we get this, which is like the core of calculus, calculating something that we can't know, that we don't know, by getting infinitely close to it. And I think that's really awesome. Taylor series make sense, actually, and are really cool.